Hey everybody, let's talk about time. Specifically, we are going to be looking at a special type of clock that is called a light clock. Basically, you've got two mirrors and you got light bouncing back and forth, and that's how you measure a tick, light going back and forth. Remember, we have Jack and Jill in this little animator here. See if they're both not moving. Their little light clock, very slow light clock, bounces, nothing changes. Now, let's try increasing Jill's velocity. It's about 75% the speed of light. And we see that Jill's light clock is taking a lot longer to tick. The duration of a tick is much longer as we observe it. And so one whole tick took 12 seconds as the stationary observer was reading it. But Jill still only got 8 seconds for round trip, which is what we saw if we were, again, stationary. I'll let the whole 8 seconds play out. Boom, 8 seconds. That's a long 8 seconds. Anyway, I hope you get the idea. And I'll show you another animation in 1 second. Okay, here's another animation of the light clock, very similar. We have it bouncing back and forth. We see that more distance is covered by the light beam for the moving object, or the moving clock. So let's take this light clock and we'll actually use it to derive what's called time dilation. Here we've got the light clock. I've got little pictures, our friends Alice and Bob, and one mirror here, another mirror there. We've got this beam of light going back and forth. In this particular picture, nobody is in motion. Now let's have Alice go into motion. She is moving at some velocity less than the speed of light relative to Bob. And we see that there's the duration of one tick, that's an up and a down, up and a down. It's one, well, it's 2 ticks that I just counted off, but 1 up, 1 down equals 1 tick. Distance of velocity, and that is going to be Bob's observation, so we'll call it TB times C, the speed of light. And so going from one mirror to the second mirror back down, that's 1 full tick. Half of that trip, CB over 2. We can define this length here as L, the height between the 2 mirrors. And the distance that the bottom mirror will traverse over the course of this 1 tick is whatever the velocity of Alice is times the measured tick duration, TB. And so we have a right triangle. A squared plus B squared equals C squared, right? So here's A, B, right? Because we're half of this whole thing here. And that's our hypotenuse. That's our first equation. Now let's see what Alice's observation is of her own clock, right? According to Alice, she is stationary. So she traverses this height, 1 tick duration. According to Alice, it's 2L over C. Because this is L, 1 full tick is 2L, divide by the velocity to get the tick duration. We'll call that equation 2. Got our 2 equations. boom, boom, boom. We rewrite equation number 2 as C times TA over 2 is equal to L. We then plug L into equation 1. We distribute the squareds, the 4's cancel. And then we can solve for the tick duration of Alice, that's TA, which is going to be equal to TB times quantity 1 minus V squared over C squared to the 1/2. We can rewrite that as TA is equal to TB over gamma, where gamma is the Lorentz factor. That's just going to be 1 over the square root of 1 minus V squared over C squared. And this is always going to be greater than or equal to 1. Again, TA is the rest tick duration, TB is the moving tick duration. So tick duration here is kind of the inverse of elapsed time, if you want to think of it as the period. And that means that we have moving clocks running slowly. Here's another way of viewing it. We've got our tick duration, capital T moving, is gamma T rest. And the elapsed time is delta T, small t, moving, is 1 over gamma delta T rest. Elapsed time observed is less, for a moving object or moving clock, is less than that of a clock at rest. And this light clock isn't special because as Alice is moving, she's just observing that same clock up and down. So too we'll actually see with any clock. And so let's do a quick example. We've got gamma equals 3. And here we kind of see the difference between the tick duration and elapsed time that I'm trying to talk about, in case you find it a little confusing, because this is kind of a confusing concept. Got moving clock ticks. So there's 1 tick, 2 ticks, 3 ticks, 4 ticks, where over the course of the rest clock, it's going to tick 12 ticks in this case. And we look at the period of the movement for moving and for rest clocks respectively. So now, does this make sense? Let's try a couple of quick examples. If V is equal to 0, we get TA is equal to TB, right? They're both stationary. Does that make sense? If V is equal to C, however, we get this like square root of 0 or 1 over square root of 0, which is a problem. And that's one quick mathematical proof to show that nothing can go the speed of light, which is actually what at least we've learned to expect. And so then that makes sense as well. Let's explore this Lorentz factor a little bit. We look at different velocities or speeds and what the corresponding Lorentz factor is, right? Speed 0, 1, that makes sense. We're going kind of fast, right? That's 1,800 kilometers an hour. But the Lorentz factor is still tiny. Right? We think of that as fast in our everyday life, but you know, I don't know how many zeros that is, but it's a lot of zeros before that 14. Then we're going 1/1000th the speed of light, still a lot of zeros. 1/10 the speed of light, 1.005. Okay, that's more like it. When we start getting above half the speed of light, we start seeing much larger numbers, right? Half speed of light, we get 1.2. For 0.9, the speed of light, it's only 2.3 though. Then we get 0.99, it's 7.1, 9999, 71. Gotta be going pretty quickly. So now I just want to highlight for you one quote from Special Relativity for the Enthusiastic Beginner. That's our kind of optional secondary text, page 78 out of the whole thing. When we're relating the times in different frames, it's very easy to get confused about where we're putting that gamma factor. The thing to remember is that if we were to proceed, the safest way is to go about it is, one, we start with the fact that if you look at a moving clock, it runs slowly, right? Leading clocks lag, moving clocks are slow, whatever phrase you want to drill into your head. Number two, identify which time is larger or smaller. And then number three, put the gamma factor where it needs to be. Remember, gamma is always going to be greater than 1. So if you need something to be smaller versus larger, that's where you are able to either divide or multiply by gamma. Feel free to check out that or the rest of this section. And that's all I wanted to cover on the light clock and time dilation. Right? This is one of the two big equations that we're going to see over the course of the semester. Well, we'll see a number of equations, but time dilation and length contraction, those are two of the pillars of special relativity. Take care.